All right, well, thank you, Isabel. Thank you, Chris. Thank you, Roberto, for giving me this opportunity. My name is Gabriel Gomes. I'm very excited about this course. It's a brand new course that the department is offering this year. Let me see if my thingy is Tools of Mechanical Engineering. So I'm going to talk to you over the next few minutes about the course, try to explain what it's about, and I'll also go over the 16 spring capstone projects. These are the ones that are associated with the course, and I'll try to explain a little bit about what they're about. So as you've heard already from Isabel, these are the tracks for the MEng program. We have the traditional faculty capstone track, which is the year-long capstone. And this year we have some pretty fantastic projects on offer from the faculty at mechanical engineering. So that's really great. You can learn more about that throughout the week at the lunch getting to know you session. So make sure you do that. But I'm going to focus right now on the tools course, this separate track, which involves the fall course called the Tools of Mechanical Engineering, which I will be teaching, as well as the 16 capstones. As Isabel mentioned, in addition to those 16 spring capstone projects, there are also projects associated with courses, I think it's 235 and 246. So there are 3 for each. So in total, that's 6 plus 16 is 22 spring capstone projects to choose from. Okay, tools of ME. So, the department, as Chris mentioned, came to me a few months ago and asked me to develop a course that would fit into this slot, this fall semester slot. And so I thought about what I would like to put into this course. So what course would have liked to have taken when I was a graduate student here in mechanical engineering around the mid-2000s? And the answer to that question was pretty easy. It came very quickly, what I would like to do with the course. So you see, I've been a researcher here since I graduated, and I've worked on several projects. I've worked with many people, different colleagues. And every time I work with someone on a new project, I get a new bit of knowledge. So you could call it a new tool. And what I do with that is that I file it in my head amongst all of my tools. And the process for doing that is to find the right location for that tool so that it is in a good relationship to the rest of the tools. And so you do this over several years, and any professor will tell you that you come up with some sort of a framework or a scaffold for the knowledge. And so that allows you to find the appropriate place for a new tool. So this comes very naturally. You will just on your own, you'll come up with your own framework. But you could come up with a good framework. You could come up with a not so good framework. And what happens is you iterate on this framework over the years until you get it right. So what I would like to do with this course is to sort of help with the framework. So why is it important to have a good framework? Well, one reason is that it helps you to learn. Okay? So when you learn a new concept, if you can associate it with other concepts in your head, then you can really get a lot of information. Say, this is a concept that belongs more or less here. That helps you a lot to understand what that concept is about and to really grasp it much quicker. So it's very helpful for learning. Another reason that it's important is that, say, you learn something new, you're presented with a new technique. You can, if you can relate it to other things, you can more quickly figure out whether that new concept is useful, or on the other hand, if it's just a gimmick, if it's just some rehashing of something old, so that you can quickly discriminate between useful information and not so useful information. That's another reason. And I'll also say that a third reason is especially applicable to people like yourselves who are part of this sort of a messy world of technological innovation. So if you want to innovate, it's very important to have a broad understanding of the different tools that are available. So how does it work? You go to school, and in school you take different courses. Courses, well, to take up on the analogy, you could take a hammering course, you could take a chiseling course, and you could take a sawing course. And say you get an A+ on your chiseling course. So you decide, well, I'm a great chiseler. I want to dedicate myself to chiseling. So you buy yourself, a set of chisels, and you start working at that, and then you discover that you really enjoy the little round chisel. And so you focus on that, and then you discover, well, I really like the 1/4-inch round chisel, right? And you narrow yourself. Then you discover, I like to work on this type of wood with the 1/4-inch round chisel and making letters and signs and so forth. So as you progress, you narrow yourself into something, and that's great. That's called specialization, right? That's what we all want to do because you need to specialize in order to go very far in a particular field and reach finally the cutting edge of that field. Say the cutting edge. And once you reach the cutting edge, then it's time to innovate, right? It will be much easier for you to innovate in your field if you still have a grasp of the larger picture. What was it that the hammer does? What is it that the saw does? So that you can bring that wider concept into the narrow application, and that's where innovation happens. So to get back to the question of what is this course about, it's about providing that framework for organizing different concepts. I'll try to provide the framework, and I will also try to give you a few concepts that you can place as sort of like an initial condition on that framework, and hopefully this is useful for you to go forward. So that's the summary of the project, of the course. Here's a taste of it. Say the set of all models. So models is probably the biggest set of tools that you use as an engineer. But there are different types of models. There are phenomenological models, and there are also mechanistic models. But within the mechanistic models, we have static mechanistic models, and we have dynamic mechanistic models. So once you have this categorization of all models, then you can start making sense of, for example, probabilistic models are a type of phenomenological models, but so are neural networks. So you start to understand those relationships. When you do stress and strain analysis of components using finite elements and the type of thing that you do in SolidWorks, it's useful to understand that this is a static model, a static mechanistic model. But the types of models that we use for robotics, these are dynamic mechanistic models. Okay? So this is just a taste of the type of thing that we'll be doing in the class. Here is the list of topics, a list of topics that we'll cover in E296MA. So first of all, programming languages. I really believe that programming languages are an essential tool for engineers. And so we're going to talk about programming languages, the ones that I find most useful for my work. These are Python, MATLAB, and Java. But this is not going to be a programming class. This is going to be, we're not going to deal with the syntax of these languages. We're going to talk at a bit of a higher level about the languages, and so that you can choose the correct language or the most useful language to apply to a given problem. We'll also talk about Git, which is the standard language for version control, another very important topic. We'll talk about the problems of statistical inference. And in that category, we'll talk about things like linear regression, hypothesis testing, neural networks. We'll have, say, homeworks where you're given a data set and you're told how to train a network to analyze that data set, that sort of thing. We'll also learn about SolidWorks and how to do finite elements analysis using SolidWorks. We'll learn how to simulate dynamical systems with MATLAB and Simulink. And also we'll learn some about optimization, how to identify an optimization problem, how to formulate an optimization problem, and ultimately how to solve an optimization problem, say with MATLAB. Again, these are not topics that we're going to delve into too deeply, but more quickly learning how to solve problems and placing them in this larger context. Okay, those are the topics. A couple other reasons why I think you should take the class that are not having to do with the material. First of all, as you know, when you enter now in August, you will have already have chosen your capstone project. So the teams will be formed. So you'll have this whole semester in the class to work with your team, do homeworks with your team, get to know your team members, and work out the team dynamic before you do your capstone project in the spring. So that's one advantage. And also you'll have a semester to brush up on your skills, your programming skills, and so forth. So these are good reasons to take the course. A few other details about the course. I think Isabel mentioned some of this. It's a 2.5 unit course. That means we're going to have 2 lectures a week. One is on Mondays, it's going to be an hour, and on Wednesdays, it will be an hour and a half. We have a great GSI who will give some programming tutorials. We'll be working with Git and GitHub, and I'm going to try to figure out if we can do some of the homework submissions through GitHub, and that might be fun. And hopefully this will be a fun course. It's not, as I said, a deeply theoretical course, but it's more trying to put some perspective on engineering. So that's the course. I'm going to go quickly now through the capstone projects that we have for the spring. And I'll start here. So Professor Michael Franklach of the ME department is offering an energy series of capstones. These projects, so you would pick one of these, biofuels, coal, solar, or nuclear, and you would then study the available information and data, study the technologies, and study the impacts on the climate and so forth. So that would be in conjunction with Professor Michael Franklach. Professor Lydia Son has put forth a project for developing a mobile app for assessing hospital-acquired infections. So hospital-acquired infections are infections that you acquire when you're in the hospital. They could come from a catheter or if you're on a ventilator, but they're a big problem. So what you would do in this project is to gather a lot of information about this problem through interviews with healthcare workers, with insurance companies, and so forth, and then bring that information together and try to develop an app that will help mitigate the problem. With Professor Horowitz, we are looking to develop a smart exercise machine. This would be, say, an exercise bike that has sensors and also actuators. And so the sensors could detect your state of fatigue and adapt the workout so that you optimize your workout. We will have available for this a experimental setup that will consist of a bicycle. And so the project will be working on the controllers and also the potential for commercialization of such a machine. Data fusion analytics to predict in-hospital cardiac arrest. This is a project that we're teaming up with Professor Xiao Hu of the UCSF School of Nursing. Professor Hu has gathered a lot of information of data of patients in the hospital as they lead up to a cardiac arrest in the hospital. And so he wants to use this data. He has this data available. He will give it to us. He wants to develop machine learning techniques to find the indicators of the onset of a cardiac arrest so that these can be predicted sooner and thus hopefully save lives. So this is with Professor Xiao Hu. Optimizing traffic signals using Wi-Fi and Bluetooth data. We're doing this, we're teaming up with a company called SMATS. They're out of Canada. And they are going to provide us with some sensors that they've developed. These sensors, basically you can stand by the road and you can detect as they go by vehicles where there's a Wi-Fi or a Bluetooth-enabled device in the vehicle. And so the question we want to answer here is whether such a device can be used to reliably measure the performance, or let's say the congestion state of the road, and then we can use that, hopefully, to pretty inexpensively optimize the traffic signals so that cities can keep their signals optimized to traffic. EcoSolar System. We're teaming up with a Bay Area company called Texas Solar. The observation here is that solar panels, rooftop solar panels, accumulate or they trap a lot of heat between the roof and the solar panel, and this heat can be scavenged in order to boost the efficiency of water heaters. Okay, so that's trying to take advantage of, trapped heat. We want to design the system based on off-the-shelf components, so that and study also the feasibility for commercialization of such a system. A point-of-care platform for performing neonatal complete blood counts with Professor Lydia Son. This is another hospital-related project. It has to do with newborns, especially kids who are born before 9 months. And when they're born, they have lots of health problems. And so there are tests that have to be performed. And one of those tests is the complete blood count. So to perform a complete blood count, you have to extract about 10 milliliters of blood from the heel of the child. And you have to do that several times a day. But the problem is that newborns, especially premature newborns, don't have that much blood, so you can't do it. And what Professor Son is trying to develop is a way to do this with much less blood. So say 10 or 100 microliters of blood. To do this, what has to be developed is a microfluidic device that can extract the blood reliably and also perform an analysis of the different cells in the blood, say the red blood cells, the white blood cells, etc. So that's a very interesting and important project. There are a lot of projects. So we have a series on autonomous vehicles that is in collaboration with Dr. Qingyao Chan of the PATH program here at UC Berkeley, of the Institute of Transportation Studies. And there are two projects, so you would be on one of these two projects. The first project is designing interactions between pedestrians and autonomous vehicles. So Professor Chan has gathered a good amount of video of people crossing the street, but really they're just jaywalking. They're just crossing the street when they're not supposed to. and then there are cars that approach them, but these cars stop sort of safely and, let's call it, comfortably, in a way that is not startling to the people. So we'd like to learn these behaviors of say, human-like driving so that they can be encoded into autonomous vehicles. So this involves learning from video. The second one is vehicle localization for autonomous vehicles based on data from an instrumented vehicle platform. This is going to use an instrumented vehicle that we have up in a university facility up in Richmond. So this vehicle has GPS, it has cameras, and so forth. And what we want to do is have a vision-based system where you can identify certain markers on the road and whose position is known, so that you can increase the precision of the GPS. So this is a very important thing that is needed for autonomous vehicles, and we'll use the equipped vehicle that we have in Richmond for this project. And finally, we have a modeling series offered by Professor Tarek Zodi, where you will apply some of the modeling techniques that you'll learn in the tools class, but you'll take it a step further to apply advanced techniques that you will learn with Professor Zodi. There are four projects in this series: modeling of laser irradiated powder, modeling of advanced lubricants for rotating machinery, modeling of plaque buildup in blood vessels, and modeling of the dynamics of swarms. So these are complex systems that require some heavy-duty modeling to analyze properly, and that's what you'll learn with Professor Zodi. So those are our projects. In summary, I want to say that if you do want to take this course track, what you should do, what you should do is sign up for one of those 16 spring capstones, or sign up for one of the 6 projects associated with ME 235 and 246, and then you'll be in. And you need to then enroll in E296MA in the fall for 2.5 units. I'm sure there are many questions about this. I will be around the rest of the week at the lunch events. I won't be there on Wednesday, but I'll be there the rest of the days. So please approach me if you have any questions.